All right, everybody, welcome back to our SPI Doppler Review series. Now that we've explored how Doppler shift is created and how it becomes a spectral display, we're ready to examine the system controls that influence what we detect and measure. So in this episode, we're going to focus on phase 6, instrumentation, and this is where physics meets the machine. We're going to break down the pulsed versus continuous wave Doppler, PRF, wall filters, sample volume, range gating, and angle correction. So examining how each control affects signal acquisition and display. Understanding instrumentation is essential because Doppler accuracy is not just about physics, it's about proper system setup. So when you clearly understand how machine settings impact velocity detection, aliasing, and signal quality, the SPI questions become practical rather than abstract. So let's move from understanding Doppler principles to mastering the controls that make accurate measurement possible. And now that we've worked through spectral, Doppler, and signal processing, let's step back and look at the full progression of the phases. So remember, we began with fluid basics, building that understanding of what blood is and what allows it to move. Then we examined flow types, identifying the different velocity patterns within a vessel. After that, we moved into hemodynamics, where physics explained those patterns mathematically, connecting pressure, resistance, radius, and flow. And next came Doppler fundamentals, where motion became frequency shift through the Doppler effect and Doppler equation. Then we explored signal processing, where those frequency shifts were transformed into spectral waveforms using the FFT. And today we transition into instrumentation. So if Doppler physics explains how motion creates a shift, the signal processing explains how that shift becomes a display. Instrumentation explains how the machine acquires and controls that information. So this is where PRF, wall filters, sample volume, again, range, gating, pulse versus continuous wave, and angle correction directly influence what we measure. Once instrumentation is clear, we'll move into clinical application where all of these principles come together in real diagnostic practice. And each phase builds logically from the last. And right now we're shifting from understanding the waveform to understanding the controls that shape it. So in this phase, we're focusing on the system controls and detection methods that directly affect Doppler measurements. We'll begin with continuous wave Doppler and discuss where shifts are detected, specifically within the overlap region of the transmitting and receiving beams. Then we'll examine the advantage of pulse Doppler, particularly its ability to select a specific depth using range gating. And from there, we're going to clarify why duplex imaging must be time shared and how combining grayscale and Doppler effect systems performance. Next, we're going to look at what determines sample volume width, including beam width and depth, factors that influence spectral broadening. And then we'll also review why echo arrival rate equals the pulse repetition frequency. This is a foundational PRF concept. And then we'll break down what the wall filter actually eliminates, right? Low frequency. So Doppler shifts from vessel wall motion. We'll discuss how the phase quadrature detector determines flow direction. And finally, we're going to examine the color priority control and how it determines which grayscale echoes display color information. So this section connects physics to system operation, helping you understand not just what Doppler measures, but how the machine controls and displays those measurements. So let's get into the first question here. So the first question is, continuous wave Doppler shifts are detected within the blank. Answer A is the range gate. Answer B is the near zone length, Answer C is region of the transmitting beam. And answer D is the overlap region of the transmitting and receiving beams. Of course, this one does have the correct answer highlighted. And so that's what it is, answer D, the overlap region of the transmitting and receiving beams. So remember, continuous wave, or CW Doppler, uses two crystals. One continuously transmits and one continuously receives. And since both are active all the time, the system detects Doppler shifts only from the area where the transmitted beam and the receiving beam overlap. And that overlapping region is where moving blood cells can, one, be insulated by the transmitting beam, and two, reflect sound back to the receiving crystal. So if you have no overlap, you have no detected signal. Now let's look and see why the other ones are wrong. So answer A said range gate. So range gates are used in pulse wave PW Doppler. So CW Doppler has no range resolution. It cannot isolate depth, so there is no range gate. Answer B says near zone length. So the near zone length is just a beam characteristic, like the Fresnel zone. So it doesn't define where CW detects shifts. Detection depends on beam overlap, not the near zone boundaries. And answer C, the last one, is says region of the transmitting beam. So this is incomplete. Just because the transmitting beam hits moving blood doesn't mean the signal will be detected. The reflected signal must also fall within the receiving beam, and detection occurs only in the overlap. So when we're looking at continuous wave Doppler, that equals two flashlights, one shining out and one listening back. So you only detect motion where the flashlight beam and the listening beam intersect. So that intersection is the overlap region. Okay, so the next question says, which of the following is an advantage of pulsed Doppler? And answer A is sensitivity of low flow velocities is increased. Answer B says higher operating frequencies can be utilized. Answer C says depth of sample volume can be accurately selected. And this one only has three. Okay. So let's look at this. The answer is obviously C here. Depth of sample volume can be accurately selected. So the major advantage of pulse wave Doppler is that range resolution, right? So the ability to choose a specific depth or range gate. With pulse width Doppler, the system sends a pulse, waits for the echo, uses timing to determine the depth. So you can place a sample volume exactly where you want it. And that's something that continuous wave Doppler can't do. So let's look at why the others are wrong. So A says sensitivity of low flow velocities is increased. So power Doppler is best for low flow sensitivity, and pulse width is not uniquely superior for low flow detection. Answer B was higher operating frequencies can be utilized. So operating frequency depends on the transducer, not whether it's pulse width or continuous wave. So this is not a defining advantage. And then D is higher frequency shifts can be displayed without aliasing. So this is actually an advantage of continuous wave Doppler. Pulse wave Doppler aliases at high velocities because of PRF limitations. So continuous wave does not alias. So this option describes continuous wave, not pulse width. And so if we're looking at comparing these by feature between pulse width and continuous wave Doppler, right, we can look at the range resolution, we can look at aliasing, we can look at higher velocities as main differences. And you can see the advantage of pulse Doppler. And then when you think of pulse Doppler, think of depth selection. All right, let's move on to the next question. And this says, which of the following Doppler techniques must be time shared? Answer A says color Doppler, B is duplex imaging, C is spectral analysis, and D is continuous wave. So the answer here is duplex imaging. It's in the name. Duplex imaging must be time shared. And why? Because duplex imaging combines the B mode, which is the grayscale imaging, and the pulse wave Doppler. So the system cannot transmit and receive both simultaneously in the same region at the same time. So the machine rapidly alternates, right? B mode, pulse, Doppler pulse, B mode, pulse, Doppler pulse. And that rapid switching equals the time sharing. It happens so fast, you don't see it on the switching, but physically it has to occur. So let's look at the other answers and look at why they are incorrect or not the most correct, or why they're wrong. A says color Doppler. So color Doppler is already integrated into the imaging system. So while it doesn't require processing, it is not classified as a time-shared duplex system in that same sense. The exam is specifically targeting duplex B mode plus pulse width Doppler. The next answer, spectral analysis, which is C. This is incorrect because spectral analysis is just a display of Doppler data over time. It doesn't require alternating imaging modes. And the last one, which was incorrect, which is D, continuous wave. So continuous wave Doppler transmits continuously, it receives continuously, so no pulsing, no switching, no time sharing. Again, it uses two crystals, one's always transmitting and one is always receiving. So if two different imaging modes must operate in the same scan line, the system must time share, and that's called duplexing. All right, moving on to the next question. The width of the sample volume is determined by the blank. Answer A says beam width and sample volume depth. Answer B says operating frequency and maximum penetration depth. C says thickness of the element and the sample volume depth. And D, the answer is number of focal zones utilized and maximum penetration depth. So this is pretty straightforward, right? So the correct answer is A, the beam width and sample volume depth. So let's talk about why that is. The width of the sample volume is determined by the beam width, which is the lateral dimension, and the sample volume depth, because beam width changes with depth. So let's go into this a little bit further. Ultrasound beams, they're not perfect. They're cylindrical. They're not perfectly cylindrical. They narrow at the focus. They widen before and after the focus. So the deeper the sample volume is placed, the wider the beam becomes. And the wider the sample volume becomes, think of the width equals the beam width at the depth. So that's kind of exactly what A is describing. B, the operating frequency and maximum penetration depth. Well, remember, operating frequency affects resolution and penetration. Maximum penetration depth affects imaging depth. So neither directly determines the lateral width of the sample volume. C, the thickness of the element and the sample volume depth. So element thickness affects frequency, and that's via resonance. So it does not determine beam width. And the beam width depends more on like the aperture size, focusing, and the depth. So this one mixes concepts incorrectly. D, the number of focal zones utilized and maximum penetration depth. So focal zones affect where the beam is narrowest, but the number of focal zones does not determine sample volume width. So maximum penetration depth is unrelated to sample volume width. So think of a sample volume dimensions in pulse Doppler as length related to controlled by pulse duration, and the width being controlled by beam width at that particular depth. So beam width changes with depth, and so both matter. Okay, first, sorry I have to make my image so small. There's no space on this slide for me to put a little cameo thing here. So the question says, echoes arrive from the sample volume depth at a rate equal to blank. And the answers available are A, the pulse repetition frequency, B, twice the pulse repetition frequency, C, 1/2 of the pulse repetition frequency, and D, 1/4 of the repetition frequency. And so the correct answer is A, the pulse repetition frequency. So echoes from the selected sample volume depth arrive at a rate equal to the PRF. And why? So in pulse Doppler, the system sends out one pulse, it waits for echoes from the selected depth, remember this? Then it sends the next pulse. Each transmitted pulse can produce one returning echo from the sample volume. So if the PRF is 5 kilohertz, then echoes from that depth are received at 5,000 times per second. So one pulse relates to one echo set, which relates to one cycle. Why are the other ones incorrect? Well, let's go over them one at a time. If you thought it was twice the PRF, remember echoes do not arrive twice per pulse. There's just one listening period per transmitted pulse. If you thought the answer was C, 1/2 of the PRF, there's no physical basis for halving, I can't even say that word. The system waits exactly one pulse cycle before sending the next one. And then D, if you thought it was 1/4 of the PRF, again, no relationship. Echo rate directly equals PRF. So PRF, the pulse repetition frequency, equals the pulses per second. Each pulse then correlates to one echo return from that depth. So echo arrival rate is equal to pulse repetition frequency. All right, let's go to the next question. And the question is, which system control eliminates low frequency Doppler shifts? And answer A is the range gate, B is the wall filter, C is the dynamic range, and D says angle correction. And the right answer for this one would be the control wall filter. The wall filter eliminates low frequencies. So remember, we talked about that. It eliminates low frequency Doppler shifts. Low frequency shifts typically come from vessel wall motion, cardiac wall motion, probe motion, patient movement. So these produce strong low frequency clutter signals that can obscure like true blood flow. So the wall filter is a high pass filter. It removes low frequencies and allows high pass. It allows high frequencies to pass. Hence the name high pass filter. So yeah, so it just means that it allows higher frequency blood flow signals to pass. And that's exactly what the question was describing. Let's look at the other answers and determine why they were incorrect or not the most correct. And so A says range gate. And the range gate selects a specific depth sample volume. It controls where Doppler data is collected, so it doesn't filter frequencies. C was dynamic range. So dynamic range controls contrast, like grayscale. It affects how many shades of gray are displayed and has nothing to do with Doppler frequency filtering. D was angle correction. And so angle correction is, this adjusts velocity calculation that accounts for Doppler angle. So it doesn't remove frequencies either. So when we have low frequency clutter, think wall motion or think wall filter. Wall filter equals, or it's correlated with removing wall motion signals. If you think wall filter, removing wall motion signals. Okay, again, so excuse me, I have to make the cameo very, very small on this slide because I don't really fit anywhere. It's a very crowded slide. And so the question is, determining the direction of Doppler shift voltage is accomplished by the blank. The autocorrelation, the spectrum analyzer, the power Doppler, or the phase quadrature. So I know it's highlighted power Doppler with a check mark on there, but yeah, the image came out incorrectly. The right answer should be the phase quadrature. And let's go ahead and talk about that. So determining the direction of Doppler shift voltage, again, accomplished by the phase quadrature detector. And to determine direction, whether something's toward or away, the system has to detect whether the frequency shift is positive or negative, whether the returning signal is leading or lagging in phase, and the phase quadrature detector compares the received signal, a reference signal shifted 90 degrees in quadrature, and this allows the system to determine flow toward the transducer, which is a positive shift, and flow away from the transducer, which is a negative shift. So without phase detection, you'd only know that motion exists, not its direction. So let's look at the other answers and why they're wrong. So autocorrelation, right? This autocorrelation is used in color Doppler, mean velocity estimation, and variance calculation. It estimates average frequency shift quickly, but it doesn't determine polarity or directly. The other answer was the spectrum analyzer. So the spectrum analyzer, remember FFT processing, this determines the range of frequencies, the velocity distribution, but direction is already determined before FFT is even displayed. And so the question came out wrong. It shouldn't have even said power Doppler. It should have said fast Fourier transform. So if I give you this quiz, the quiz will actually have fast Fourier transform in the answer as one of the possibilities. And just remember that FFT converts time domain signal to frequency spectrum. It shows magnitude of frequencies, but direction detection happens earlier via that phase comparison that we spoke of. So phase quadrature detector, that determines direction. Fast Fourier transform that builds the spectral waveform. Autocorrelation estimates mean frequency, so the color Doppler. So if the question says direction of Doppler shifts voltages, think phase quadrature detector. Well, all right, we are on the last question of this section, and let's go ahead and get started. So the question says, with color Doppler imaging, the priority control blank. So the answer A, it says eliminates aliasing. So the priority control eliminates aliasing. Or B, filters out low intensity echoes, or C, selects the pulse repetition frequency, or D, selects which grayscale echo strength will demonstrate color. All right. And so again, the correct answer is D, select which grayscale echo strength will demonstrate color. The priority control, it's also called the color priority or the threshold. This determines which grayscale echo amplitudes are allowed to display color. So in other words, strong grayscale echoes like vessel walls can suppress color. Lower grayscale echoes like blood are more likely to show color. And the priority setting adjusts that balance, and it tells the system at what echo strength should color be displayed. And that's exactly what answer D is describing. Let's talk about the other answers here. So A says eliminates aliasing. So aliasing is controlled by the pulse repetition frequency, the baseline shift, and using the continuous pulse instead of the pulse width. Priority has nothing to do with aliasing. Filters out low intensity echoes, as said in answer B if you selected that. So that's more related to wall filter and gain adjustments. Priority doesn't filter low intensity echoes. It determines whether color is overlaid on certain grayscale strengths. And the last answer, if you selected C, selects the pulse repetition frequency. PRF is controlled by scale control and depth. So priority does not affect PRF. So think of priority like a traffic cop between grayscale image and color Doppler overlay. It decides which echo strengths get color and which stay gray. So that's it for this section. I want to thank you for making it to phase 6, and we will be concluding this review on the next section, phase 7, Doppler modalities and clinical application.